All right, so these are what is normally called difference of squares quadratics. And the reason for that is if you look at them, they are all perfect squares. And if you forget what a perfect square is a number that you can take the square root of and get a number, a whole number, out. So this means that 64 comes from 8 times 8. It's the same number. So if we take the square root of that, that's where we're getting 8. Whereas like the number 65, I'm sure we could find stuff that would be multiplied to 65. So like 6 times, or sorry, not 6. 5 times 13, for instance. 5 times 13 gives us 65, but that's not the same number. And I can't just take the square root of that because I'm not going to get a whole number out of here. So let me just do it real quick on my calculator. If I take the square root of 65, I get 8.06, somewhere close to 8 because 65 is close to 64, but it's not a perfect square. So again, a perfect square, when you hear that, is it means that when you take the square root of a number, it comes out perfectly. So there's two ways to do this. The first way I'm going to do it is what's known as difference of squares. The way that we've been doing them is factoring by grouping. Doing it in the difference of squares method, though, is faster, as long as you know what your perfect squares are. So I'm going to ask myself, what times what, which is the same number, is 25? And my answer to that is 5. 5 times 5. And then I'm going to ask myself, well, what times what is x squared? X squared is actually a perfect square also because it's x times x. And then I'm going to ask myself, well, what's the perfect square of 16? What times what gives me 16? That's the same number, 4 and 4. Okay? I know that this is going to break up into two binomials like almost all of our factoring problems do. I'm actually going to put this stuff over here. So 5x goes in the front, 5x goes in the front, and here, since it's a second, it goes second. So 4 then goes here, and another 4 goes here. So now I see if I multiply this back out, 5 times 5 would give me 25x squared, and 4 times 4 would give me 16. So it's looking good so far. But I need a negative 16. A negative times a positive gives me a negative. A positive times a negative gives me a negative. But I cannot use two positives because that would give me a positive, and I cannot use two negatives because that would give me a positive. So I can't use either of those. So I'm just going to make one positive and one negative. And that's why it's called the difference of squares, because all of these you see here, all of them are minus. All of them are negative. So if you ever see perfect squares with a subtraction sign, that's when you know to do this method. So now I'm going to look at the next one. The next one is x minus 16. So I'm like, okay, well, what's the perfect square of 16? We just said it was 4. And we just said the perfect square of x squared. Oh my gosh, I'm trying to change the color to blue. What's happening? I want you on blue. Okay. X. It's still not tiny though. No, it is. Okay. So 4 and 4. And also we notice our quadratics are usually in the form of ax squared plus bx plus c. We have no b value here. So hopefully you can identify b as being 0. So that's why it also makes sense to have one of these positive and one of these negative, because negative 4 plus 4 or 4 minus 4 is 0. So I just gave you two reasons why it makes sense that we use a positive and a negative when we do these. So next one, I see 4. The perfect square of 4 is 2. 2 times 2 is 4. Perfect square of x squared is x. Perfect square of 9 is 3. Notice how each of these binomials are the exact same terms. It's just one is negative and one's positive. Here I have a 5x, here I have a 5x, here I have 4, 4. One is negative, one's positive. 4, 4, x, x, one's negative, one's positive. 2x, 2x, 3, 3, one's negative, one's positive. Okay, so I'm going to do these last two by factoring by grouping. So if I wanted to do this one by factoring by grouping, I would say, okay, let's multiply my a times my c value. That gives me 49. And I would say, what are the factors of 49 that can give me 0? Because again, remember, my b is 0 here. So what are the factors of 49 that can give me 0? Well, 7 times 7 is 49, so it would have to be a negative 7 and a positive 7. So I rewrite my ax squared, and then I separate my b value into negative 7x and positive 7x, and then I bring down my constant. Now I group them, and I factor out what's inside. I factor out the greatest common factor. So I have an x over here that's in common, and I'm left with, my parentheses are coming out as straight lines, x minus 7. Between 7 and 49, I know I have 7 in common. So x minus 7. And now I see the thing that we keep looking for when we do factor regrouping, that I end up getting two matching terms. So now I factor that out, x minus 7, and I am left with x plus 7. Okay, so same thing as up top, just a little bit longer. All right, and then coming over to this one, I'm going to do it by factoring by grouping again. So this is going to be annoying, though, because I'm like, all right, 25 times 36, got to pull out my calculator. 25 times 36 gives me 900. 900. Well, I know that 3 times 3 is 9, so I'm like, all right, let's see. 30 times 30, perfect, that works. So I know it has to be the same number, and again, the reason it has to be the same number is because one has to be positive and one has to be negative for them to cancel out to 0. So I get 25x squared minus 30x plus 30x minus 36. I know it's getting a little sloppy, sorry. So I see on this side that 25 and 30 have 5 in common. They also both have an x in common. And then I'm going to factor that out, and I'm left with 5x minus 6. And once again, over here, I'm looking at what do they have in common. 30 and 36 both have 6 in common. So I'm going to factor out a positive 6. And I'm left with 5x minus 6. And again, I see, oh, okay, cool, I have two matching terms. I factor that out, and it is the same as the ones up top, just a little bit longer way to do it. 5x minus 6 times 5x plus 6. There we go. And that's it. So you can do it by factoring by grouping, or you can do it by the method above. Okay? Either way, you need to identify that these are perfect squares that you're dealing with.